Hi, my name is Stuart Halloway, and we're going to be talking about concurrency in Clojure. And before we even start, I want to go to that most important resource of all software developers. I'm sure you have this on your desk, the Oxford English Dictionary. And the OED tells us that concurrency means the coincidence of events or space. So it actually means things happening in the same place or things happening at the same time. And there's a closely related word, parallelism, which the OED tells us is the execution of operations concurrently by separate parts of a computer. Those guys are really up to speed, keeping track with technology. Now, the problem with these definitions in the OED is that even as programmers, we're often confused by the differences between these two terms. And so I'd like to start by clarifying how we're going to use them here, which is also, by the way, the correct way to use them as ordained by God. So it's a useful thing to know. So concurrency is really a property of the system that you are modeling, right? It's saying that different things are happening at the same time. So I would like to book an airline ticket to fly to Atlanta to speak at DevNexus, and somebody else would also like to book an airline ticket to fly to Atlanta and see some golf. And we are both potentially concurrently looking at the same flight or the same seat on the same flight, right? So it's a property of the problem domain. Parallelism is really an implementation technique. So it's not so much when I'm doing something in parallel that I care that it happens in parallel, but I do care about something. What is it that I care about? I don't really care that it happens in parallel. I care that it happens fast. So if there was a genie who could do all my work in 1 microsecond and that met my SLA, I don't really care if the genie does things in parallel or not. Parallelism is about how we handle things that we may need to use concurrency in order to make fast enough to meet requirements in our application. So concurrency is likely to be an implementation technique for big problems that we're going to chop up and do in parallel. But these are really separate things. This talk is a talk about the first thing. It's a talk about modeling domains where there are multiple things going on at one time and how to use language constructs to do that. Having said that, if we have time at the end, we can talk about the other one too. So don't get all dejected if you came here looking for parallelism instead of concurrency. The techniques that you use for concurrency are going to overlap heavily with things you'll use when you're doing things in parallel. So some of the things I'm going to show you today, you're going to go, of course, if I wanted to do a bunch of work in parallel, that would help me. Now, we have a set of tools as programmers that we can use to deal with things that are concurrent. The first tool that I want to talk about is threads. Right, so we have this notion that there can be more than one flow of control through our application. And as machines become more and more multi-core, this virtual flow of control in parallel or concurrent is actually also a physical concurrency. We also have, and I'm going to use that sort of open little bucket there with the angle brackety looking thing underneath the number 42. We have places where we can put stuff. That's a technical term that I'm introducing today. Places we can put stuff. And places include things like memory on machines and registers and L1 caches, but places also include storage. And in general, we are used to modeling our system with a bunch of places that, except for the memory to storage divide, are relatively homogeneous. Right? So I have 32 gigs of RAM on my machine. I don't get all bothered that I made something and it landed in that first gig as opposed to landing in the 5th gig of RAM. They're all the same. I don't really care. They're just places. And the same place can be used for different things. Right? The places in RAM are not labeled. Int goes here. String goes here. Languages come back and apply that labeling as a level above that, but at the hardware level, right, they're not labeled in that way. They are labeled physically, perhaps, right? They're of a certain size and whatnot, but they're not labeled for their purpose, these places. Now, that's great. These two things give us the tools we need to make a bunch of stuff happen all at once. Right? I can start a bunch of flows of control, and they can bang away at places. The problem is, what happens when they have multiple threads in multiple places? Now the concurrency takes a sort of plot twist for the negative because they can get in each other's way, they can confuse one another. One thread can be changing a place while another thread is also changing the place. And remember, these places can be small. They can hold something like 42, or they could be really big. Right? We could imagine a whole range of memory, so a whole megabyte of stuff. So I'm cranking through the front of it, and some other thread is cranking through the other end of it, and then we collide, and both of our jobs... Well, here's the thing, right? One of the nice things about concurrency is that if you get it wrong, the program immediately stops and doesn't yield bad output. I have a habit of lying on stage. Right? What happens if we get this wrong? We don't know, right? It's arbitrary failure. In my experience, when we get it wrong, the unit tests can't catch it, but the client review can. Or, for instance, or going to production can. So getting this wrong can be a real problem. And we have a whole bag of different computer science techniques that I'm going to unfairly all lump together under critical sections for now as a radical oversimplification, as some sort of way of saying, I'm going to put a protective boundary around something that I'm working on, right? These two 42s, these two boxes, I'm going to draw a dotted line around them and say, I'm only going to let one thread in. Or it's a semaphore, I'm only going to let 5 threads in, whatever. I'm going to have some sort of control that's going to keep things from going wrong. So there is a brief and brutally unfair summary of the tools that we have at the bottom for dealing with these kinds of things. Then we have information that we want to think about. And information that we want to think about kind of comes in two flavors, memory and records. So let's think about how memory works. We all have memories. I have memories. You have memories. We can have memories of the same event. When we have memories of the same event, we probably agree, broadly speaking. Right? So if somebody asks us after the talk today, what was the temperature of the room between 60 and 90 degrees Fahrenheit? We're probably all going to remember that it was, unless something radically changes, and I hope it won't. Although 59 wouldn't be too bad. 91 would be more Atlanta-ish. So we have these memories, and then there's this notion of taking memories and making them into records. And if you look at where the word record comes from, it actually comes from the notion of a court of record. Right? The idea of records comes from doing legal things and saying, we are going to say that this is authoritatively the case. What makes it authoritatively the case?
Somebody said so.
You wrote it down. Somebody didn't just say so, they wrote it down. And so there are, in fact, courts not of record. And so has anyone ever been before a court not of record? So if you go before a court not of record, the judge decides based on his or her memories. Right? That's all they have. There is no record, and typically there's a divide in the legal system such that things for which you could go to jail or be fined money have to be before courts of record, so that you can come back and look at the records and appeal later when you say, I'm not supposed to be in jail sitting under this $1 billion fine. I'm supposed to be somewhere else. So those are the kind of real-world ways that we think about information systems. And a big difference is memory just represents the sort of remembered perspective of an observer, and records represent some notion of an authority. Who plays the role of an authority in our software systems for these kinds of things typically? I'll make it a multiple choice question. I can see you guys are a little tired. The web application server, or the CSS style sheets, or the database. The database often acts as a system of record. We say that if the database says this and the cache says that, then the database is the record and the cache must be broken in some way. So we have these two ideas. Now, the question is, how should we model these memories and records on the computer? And what happened a while back is that we made this decision that memories and records were going to be modeled by places. So those little buckets that you can drop things in, and this is true both in memory and on disk, right? There are places where you can put stuff. And the reason that we did this, the reason that we made memory and records equivalent to places, is that memory is really tiny and expensive, right? I mean, having anything more than a few hundred K of memory is, exorbitantly expensive. Storage is also very small and expensive, right? When you store things, you have to put them onto a cassette drive, and it makes that irritating ka-ching, ka-ching, ka-ching noise. So that's also extremely expensive. And machines are precious dedicated resources, right? So it makes sense to go to a place because machines are themselves sort of exotic destinations, right? This machine on my desk is serving the web server, right? They're not these sort of ethereal things, appliance-like infrastructure. They're these dedicated places. And applications have complete control of the world, so we can manage all of these places. When were these assumptions true? A while ago. I'm going to go mid-70s. These assumptions were in their heyday. Right? And the problem is that our mainstream programming languages have not adapted at all to the fact that these things have changed. Not one whit. C, C++, C#, and Java, which I'm just going to enumerate as the big programming languages. And if you don't believe me, go and search on the internet. Right? Those are the big programming languages, and they all embody this attitude that we're going to model memory and records with places. And this attitude grew out of the characteristics of systems in the 1970s and has generally moved along unconsidered since then. So we're going to take a different approach. Instead, we're going to say that new memories have to use new places. So every time I want to make a new memory, I put it in a new place. Likewise, new records have to have new places. Every time I want to make a new record, I'm going to put that in a new place. New moments in time have new places. So if I have some idea of a fact yesterday and a different idea of that fact today, those are going to be stored in two different places. We are just not going to reuse places, period. Right? Place reuse, bad news. Place reuse makes sense when you have a few thousand places. Place reuse does not make sense when you have a few trillion places. It's an extremely bad idea. And everything that used to be done all over our systems, this in-place change, is going to be encapsulated by constructors. That's the only place things are going to be allowed to change in place, is when we're making stuff, as an implementation detail inside of making stuff. Now, it turns out that we're extremely well positioned to adopt this model for one reason. Right? Computer science, as used by business and industry, has improved, in my opinion, in one key way in the last 20 years. And that is the rapid rise of use of garbage-collected languages. Right? If you run in a garbage-collected language, then it's possible to model the world in all these ways. Right? You can make new memories use new places. You can make new records use new places. You can make new moments use new places. And if you ever stop caring about old memories or old records or old moments, you stop referring to them, and eventually what happens? The garbage collector makes them go away. Right? Now, the interesting thing is that we got through phase one of adopting garbage-collected languages. Right? We now use them to manage memory for us. But we haven't really absorbed the modeling implications of having garbage collection. And in a large way, that's what this talk is about. So, if we're going to go down this road, and we're always going to use new places to make things, then the things we make our programs out of are going to be values. And values are going to be immutable, which means they never change. They are going to be potentially lazy. This is a really nice property that never changing gives you. So let's say that I have a value that is a terabyte worth of stuff. You may not have a terabyte worth of space to contemplate that value, but I can deliver it to you lazily because we both know there's no place we have to go to make sure the value is sound because it's immutable. So values can be lazy. They can be cached forever for the same reason. Right? If we've agreed that this is the value, we can cache it forever. And they can, of course, be arbitrarily large. Now, the important thing about all this is that I'm not naively suggesting that if I have 1 million things in my address book and I add one more, that we take a linear hit on the size of the address book to add that one more thing. Right? That would be a naive approach to using space. Because these things are immutable, they can also share structure. So I can say, I have my address book database with 1 million things in it here. I have my address book database with one new address added over here. And for the 1 million things, they actually share structure. There's no possibility for conflict because we're not thinking in terms of places. So we can model things in that way, and it's actually efficient to build these kinds of data structures. So having said that, what can be of value? I'm going to show values as boxes. They're nice and solid and reliable. They're not open like those creepy places where threads can just walk in and do whatever they want. And the act of closing the box around the value is the act of construction. right? When we construct a value, we've put that box around it, and now we say we're never going to touch it again. So what can go in there? Well, obviously, 42 could be a value. Everybody knows that in the first data structure you ever make always has to be 42. But the value could be more complicated than that. So it could be a map. So here's a map with key first name Stu, value Stu, key last name value Halloway. That's also a value, even though it's composite. So even though something is composite, it can still be a value. And of course, once it's composite, it can be quite big. So has anybody ever used the MusicBrainz database? It's got, I don't know, maybe 100 million records, something like order of 100 million records in it. Right? That whole thing could be conceived as a value. Right? It is a value. Now, as new music is added to the database, it takes on new values, but there is a value of that. And of course, once you go there, you could say that the entire Wikipedia can be conceived of as a value at some point in time, or in fact, the entire state of the physical universe could be conceived as a value. So can anything be a value? Is this so who loves this right now? Which despised, unloved corner of the computer science world is cheering at this notion? All the functional programming people, right? All the FP people are like, yeah, damn straight, I've been telling you that for like 20 years now that you ought to program this way. They're really excited about this. But the fact is that not everything is a value, not everything is a pure function, so you need something else. And the something else is, we're going to introduce another term, a reference. So a reference is just something that can refer to things. That's it. Right? And it can refer to values or potentially to other references. But importantly, these references allow only atomic functional succession. It's not that open world of places where just anybody can reach in and do anything. The only thing you can do to these references is take it from one state functionally and atomically to its next state. So that's why I use the word succession, from one point in time to the next point in time. And because I just said time, right? Because you have these things that can point to other things, and they can have successors, right? I could say, well, right now my value, Stu's weight is 184, because he is kind of in hibernate mode for the winter. But I'm really optimistic that in a couple of weeks I'll start running more, and my weight will drop to 178. Right? So you could have a reference that represents my weight, and then that reference right now is 184, and maybe in a few weeks from now it'll be 178, and so on. And so that gives you a notion of time. Right? You now have this notion of, at a certain point in time, this value pertained, and another point in time, that value pertained. And from time, we perceive identity. Right? So if you watch me walking around up here, most of you probably perceive one human being walking around. So there's an identity, me, which you associate with the photons hitting your retina and the interpretation of them. You probably don't see arbitrary swatches of color that you can't interpret separately and sort of, unless you're mentally ill in some way, you don't perceive the world that way, right? You're going to see, so we make identities out of successions of values. Right? If you see something and you see something else that looks similar but a little different, and something else that looks similar and a little different over time, you go, oh, that must be something moving through the physical world. And of course, one critical notion about these references is while they have these carefully defined rules, which is that they refer to things and they only have atomic succession, they are compatible with a wide variety of, and I'm going to go back and take that word update out. I'm never using that word again. I've been auditing slides. They are capable of a wide variety of succession semantics. Right? There are different ways that these things can proceed to their next value, but there are never updates. So, let's build this up. We're going to start with some values. These are good immutable bricks, building blocks. So we can imagine these values are, for example, 42, 43, and 44. So they represent something that's growing over time. We then have the notion of functions that we can apply to take one value and get a new value. So here I'm going to imagine that f1 takes v1 and gives me v2, and f2 takes v2 and gives me v3, and so on. Those changes are atomic successions, right? So so this is atomicity in the transactional database-y kind of sense, right? For from the point of view of anybody who's observing references, they don't ever see anything but V1, trapdoor through to V2, trapdoor through to V3, and so on. And so the box that you put around all this activity, this dotted line that protects this succession of values, is what we call the reference. Now, this has either radical or entirely intuitive properties, depending on how you want to think about it. And those properties are that observers can perceive the identity, right? So an observer looking at this can say, oh, there's this thing that's changing from V1 to V2 to V3 over time. But they can also remember past values. So I can watch it change, but I can hold on to value 2 if I'm interested in it and keep thinking about that. Or I can hold on to all the values and keep thinking about them as long as I want. Which, by the way, is how physical reality works. Right? As I walk around the room up here, you're all looking at me. Until you get down to a quantum mechanical level, the fact that you are all looking at me imposes no particular tax on my activity. Right? You can all be independent observers, and you can all form memories, and your memories are not places in the sense that your memory will be corrupted if somebody else wants to remember me differently. And so these observers, and the little triangular wedge thing are supposed to represent like eyes looking at things. These observers don't have to coordinate with each other or even be aware of each other's existence. And of course, when somebody stops observing one of the particular old values of a reference, what eventually happens to it? Garbage collection, right? Or, hardware keeps getting faster so quickly that we don't even bother to have a garbage collector and it just is there. Who knows? But for now, probably garbage collection. So that is the epical model of time. That is the sort of reference succession model. And this is how Clojure works. If you understand this, you vault to the top 10% of Clojure programmers immediately, because this is the core idea. The code does not matter. And in fact, the code is remarkably simple to read once you are holding this model in your head. So let's go and look at some of that code. So here's some API. I'm going to define a counter. So this first line defines a reference called a counter. And the reference constructor is called atom. So an atom is a particular kind of reference with particular semantics, which we'll talk about. An atom represents synchronous, uncoordinated box in which something sits. Uncoordinated means that I can't coordinate its change with anything else. Synchronous means that if I want to change it, I'm going to get back the answer of what it changed to as part of doing that operation. Right? So it's synchronous, coordinated change. I'm then going to model change by passing a pure function. So plus is a pure function, and maybe some args. So here's plus 10. So I'm going to say take whatever is in the counter and plus 10 it. And then that verb in front of counter, in this case swap, has atomic succession semantics. And these verbs vary. So you can have different verbs in this spot, and which verbs are legal depends on which reference type you have. But once you have the basic model, you're done. Right? There are now a half dozen different reference types and dozens of verbs that can be applied here, but they all work exactly the same way. They all guarantee functional succession from one value to another. So now let's take a look at bigger structures. Now instead of the value 42, I'm creating a person. So now imagine that you're building the traditional web application and you're modeling your customer records in the database or whatever. You've got a create person function that makes a person, and we stick that person in an atom. And now we're going to send that person an entirely different function. We're not going to send that plus 10 because plus 10 is not interesting or relevant for person objects. We're going to send it assoc name John. So associate the name field of this person with John. You can also have varying semantics. So now we're going to have a promise. A promise is a different kind of ref. It's not like an atom. A promise says, here is a reference that will only ever take on one referent. And I promise that somebody will make it available at some point in the future. Right? Via some mechanism, which we don't even have to talk about right now. So a promise only represents the potentiality of getting something in the future. And then deliver, oh, now I will talk about it. Deliver says, OK, make this promise complete. So this is a mechanism for throwing off work that somebody might complete later and then being able to go back and get it. This model not only extends throughout Clojure, but it can also be used in your own applications, and you can create your own new types that have these reference semantics. So for the last couple of years, I've been working on a database called Datomic. Datomic is written in Clojure, and it has Clojure semantics. So it has values, and Datomic has one value type, the database. Right? The entire database is a single value, and it actually has only really one update semantic, which is transact. Right? Do an ACID transaction on this value and give me back a new value. And so the entire database case looks a little bit more elaborate to set up because it's persistent. Because this is, all the other refs I showed you before were transient in-memory creatures. Because this one is persistent, there's actually two steps in getting it. There's make it and connect to it, because you could actually connect to one that somebody else made. Right? So you want to break that out into two separate steps. But when you look at the actual semantics of operation, it's actually simpler than the in-memory reference types, because you don't have to pass a function. Transaction can do only one thing, and so we left out that function. Right? We could have had a function there called grow, or something like that, that said, the database should acquire new information, or whatever function you wanted to call it. The other reason that there's no function name there is that Datomic is a Java API with a parallel Clojure API. So this API maps exactly to a Java API, which is connection.transact some data. And if we put that function argument in there just to make it look like everything else, then there'd be a ton of explaining to do to a Java programmer, because they don't have access to any of these other reference types. Right? So to them, that story doesn't necessarily add any value from their language. So now, there are a ton of different types. And when I used to talk about concurrency and Clojure, I actually spent most of the time in the talk with dozens of slides going through all this. And I'm not going to do that anymore. There's just one slide about it. I will talk about it for 10 minutes or so, but I'm not going to do that anymore, because you can look all this up in the docs. Right? You have the mental model now, and the mental model works the same everywhere. But let's talk about the differences, because these differences will get to how you start modeling applications. So agents represent asynchronous action. So I'm using the sort of single arrow pointing one way to represent async, and the arrow pointing this way and the arrow back to represent synchronous actions. So agents represent async. I want somebody else to go make this value succeed to something else. Right? The counter is currently 42. I want the counter to become 43, but I can't possibly afford to take the hit of doing an add operation on this thread right now, so I'll send it somewhere else. Okay, that was a ridiculous example. Right? Because the hit of an add operation is smaller than the hit of throwing something off to a different thread. But you can imagine something bigger. Right? Some sort of bigger thing you want to keep track of. And all of the different agent functions have to do with which thread pool the work eventually gets done on. So when Clojure first had agents that had send and send off, send puts it on a thread pool that is calculated based on the number of processors you have on the machine. So the idea is, if you're doing something calculative that you want to defray and send into the background and have succeed a value in the background and then go back and get it later, you use agent send. And because agent send uses a processor-bound thread pool, you won't overwhelm yourself. Right? If you send too much, it'll just pile up. Right? They'll back up and wait. They won't all, more than your processors won't run all at once. But then, of course, people would say, well, I have tasks that are not processor-bound, they're I/O-bound. Aha! We have special sauce for that too. Send off has an unbounded thread pool. Right? So if you're doing a bunch of I/O stuff, you can knock yourself out. You can send a bunch of things that'll block and tie up 100 threads or 1,000 threads or 10,000 threads, or oops, your VM falls over. So send off is really great. But if you're doing a high-performance application and you start to really care about the exact details of your thread pool, eventually you say, you know what? I don't want to be driven by some Clojure language developer's notion of what thread pool I should use. So send via actually takes a specified thread pool. So you can say, do it on this agent, but use the thread pool I provide, because I know exactly how my application works, and I want to make sure that my application has no more than 50 and no less than 38 threads assigned to this task at any given time. And I've figured that out based on my detailed profiling or towering intellect, or however I figured it out. So atoms are synchronous. They're the smallest and simplest one. Right? These are the smallest and simplest ones. These are really simple compare and swap constructs. And so what atoms give you is compare and set. Right? Update this if the value before was this. right? So it's like conditional put, if you want to think of it that way, right? Say, if the value was 42, make it 43. So I want to make sure that nobody else got in before me. Swap says just do a functional transformation. So swap says add 1 to this. Which one of those things is more efficient? Swapping and saying just add 1 to this regardless of what it is, or saying if it's 42, take it to 43, but otherwise fail? Swap is more efficient, right? And on the flip side, so why don't I use swap all the time then? I may have an application where the semantic requirements are I have to transition from A to B. If the semantics are I must go from A to B and I must know I was coming from A, then you need the compare and set. And then reset is boring, it's degenerate, right? Reset is just that function of the old value which ignores the old value and sets it to something. So good old-fashioned, old school setting things. Datomic connections, so that's not part of Clojure but part of Datomic. They provide ACID transactions as their semantics. So things are have the ACID properties, and they can be done synchronously or asynchronously. So there's transact and transact async. We have a question on the floor. So the question is this implemented in terms of the underlying platform's capabilities to do that? Yes, it should be. It is in Clojure on the JVM, and if you're porting Clojure somewhere else, the point of these things is to be able to target the platform capabilities, and we'll come back to that a bit later. But yes, you should presume that if there is an efficient way to do this that uses an underlying platform resource, that's why it's done, and so that those are done correctly. And if you ever find one that isn't, you should file a bug. But that one does, in fact, work that way. So then you have refs. So I have this love-hate relationship with refs. Refs are software transactional memory. So refs, unlike atoms, allow you to do coordinated change. You say begin transaction, and that's not actually the API name, but we'll just say begin transaction, and then you say do something to a ref, do something to another ref, do something to a different ref, and then all those changes are coordinated and either succeed together or fail together. So what you would expect out of a coordination mechanism. When Clojure first got hot, when it first bubbled onto the radar of Java developers everywhere and Hacker News and those kinds of places, people were all excited because software transactional memory was the second coming of all kinds of awesomeness, and people got very interested in this. And it's really cool if you need it. I wrote several STM transactions when I was writing the book on Clojure. I have never written an STM transaction since then. Your mileage may vary, right? My point is that these things serve different roles, and so depending on what kind of thing you're building, different ones of these are going to make sense. And the important thing, if you're in a barroom argument about concurrent programming, which judging by your general fashion sense, I can imagine happens to some of you, if you're in a barroom argument about this kind of thing, which I would get into as well, then the important thing about Clojure is not software transactional memory, which is what people got all excited about. It's the fact that it has this whole slate of tools that implement a unified programming model. The final guys, vars and var bindings, have to do with how you manage the global namespace of a Clojure program. So a Clojure program is divided up into namespaces, which on the JVM will correspond to Java packages. And the top-level names that constitute your program are namespace names in those packages, and they're stored in vars. Vars are reference types, and the only place where you would modify a var, the only place where you would call alter var root, is if you were doing application configuration stuff. If you were doing things that were the equivalent of dynamically changing the class path in Java to load a new version of something in production for some reason. The most common use of that I've seen actually in the wild is everybody, the first thing they do when they learn a new language is write their own testing framework. And the first thing they do when they write their own testing framework is write their own mocking and stubbing framework. And so people use alter var root to say take something in the system and make it work a different way for the duration of this test. It's not necessarily that widely used in production. And then var bindings are a little bit different than that. You can set metadata on a var in Clojure that says this var is dynamic, which means it can be set in a local binding context. So you can set it on a particular thread, and that setting is invisible on that thread, and the tree of threads spawned underneath that or accessed underneath that to do some job. So I actually want to call it binding local and define binding instead of, say, thread local, because it starts on whatever thread you do it, but if that thread then asks an agent to do something, that agent will be able to see that binding even though it happens on a different thread. So it's a flow of control notion as opposed to just a thread local binding thing. Again, that's not used hugely often. the point of, one of the key points of all this is to be as functional as possible, right? So while we don't agree with the functional people that you can be all functional, you want to be as functional as you can. So unless you have an identity to model, you don't want to be in the business of just changing things. And so, swapping vars around and making them bind to different values is another recipe for introducing undetectable or hard to detect change in your application. So you won't see it a lot. An example of where you might see it is when you're at an interactive shell, you can set the print length of something that interactive shell will print. Right? That's your thread on your shell, and you want to say, you know what, I'm talking to a database with 1 trillion things in it. When I print it, I'd like you to print the first 5 of them and then an ellipsis. So set print length 5, instead of try to print 1 trillion of them and then I have to shut down and go restart the process. So that's the update side of things. All these different refs have some abilities in common. So the most important thing you want to do as a reader is get the value out. And to get the value out of a ref, you deref. This is considered such an important operation that it has syntax sugar. So you can say parentheses deref blah, or you can just say at blah. Get the thing that's at this ref. You can also specify for a reference a validator. That validator is a function that guards succession. So when you say atom0, validator integer, that says this atom is going to have 0 in it, and don't let anybody ever change it to anything from which integer will return false. So it will call the function integer on the result value inside the atom, right? Again, preserving all these semantics, right? This is part of that atomic succession. And if that fails, then it won't take on that value. Also, what is a system of references without the ability to sort of watch them from afar or be notified? You can add to any of these reference types a named watcher. So here, watcher is a function, and a/name is the name I gave it. So I'm going to name this thing a/name, and then if I'm tired of watching that var or ref or atom or whatever, I can say remove watch. All these capabilities are common because they all have to do with reading things out, and these things don't differ. Right? Atoms and agents and datomic database connections, all these things work in the same way. So conceptually, these things are all the same. There is another set of reference types that I'm going to call the pending references. These are references that also implement, at the Java interface level, an interface called clojure.lang.ipending, I believe. And they represent work that may not be done yet. Because they represent work that may not be done yet, they're primarily about letting you wait on something being done. And so they will only ever refer to one thing. When you create them, they are in what is called an unrealized state. So they don't refer to anything yet. And then, when they're done acquiring whatever value they're going to acquire, they are realized. Because of this, I don't really think of these as identities. Right? I imagine identity as the notion of change over time. I guess if you think of that, the degenerate case of something that can only change once and never changes again as still being an identity, it's a little bit of a semantic discussion at that point. But I don't sort of conceptualize them in my own head as identities. And right now there are 3 of these pending reference types in Clojure. There's a future. So here I've got some task that takes a long time. And so I say, put result in, darn it. So this would look a lot better if it actually had a call to future around it. And this laptop crashed earlier today at lunch and destroyed those changes, which is extremely frustrating. So I now know the syntax errors on the next 4 slides because I fixed them at lunch today, and then this laptop crashed and threw them away. So you need to have def result future of that. So this work is going to execute on a pooled thread. And then the difference with these pending references is because they might not have a value when you first get them, you can wait on them. So you can say, I want to get me back this result. I'm willing to wait 1,000 milliseconds. And if that doesn't happen, if it's not ready by then give me back whatever or else refers to instead. And of course, if I'm feeling dangerous, I can just do a regular deref. Right? Again, I can do deref or @, just like the other reference types. And this will wait forever. Or people who know Java programming under the hood, it'll wait forever or until what happens? Somebody interrupts the thread, right? Somebody could interrupt the thread, but it's not going to stop because you didn't do the work. So you should be careful with using that. There's also a type called delay. Again, this thing needs to be inside of a call to delay. So def result, parentheses, delay, that stuff. Question from the audience? It returns whatever or else refers to. Yeah, so the question is, if we time out on one of these futures, what do we get back? That's the purpose of the third argument. And this is a very common idiom in Clojure. So you're going to see, do something with some condition, and then the or else value. It could be the literal 10. In this case, it's a symbol, so it points to something else. It points to something not defined on this slide, right? But it could be a literal 10. It could be a string. It could be anything. One of the key goals of programming with data and programming in a Lisp is everything composes. So if there were any arbitrary rules on what that could be, it would kind of suck. And it doesn't kind of suck. It's kind of awesome. But only kind of. And again, this is true for all of these types. So result, delay of something I don't need yet. The way a delay works is it just caches that body, and it doesn't actually do the work until you ask for it. And then after one person asks for it, if anybody else asks for it, they'll get it immediately. And of course, you have the same ability to wait for it forever if you want.
Is that again missing a delay?
Yes, all of these are missing. These 5 slides are all wrong. I will post a link at the end that has the actual calls, the factory calls that makes all these guys. I actually don't know how to type, so I could fix it on the fly if I did, but I can only type about 1 character per minute, so it takes a long time. So the final one is promise. A promise takes a no-argument constructor. You're not setting up any work to be done later. You're promising that somebody else will do the work later. So that just creates a reference, again stored in the var named result, and then at some point in the future, somebody had better deliver the result. Deliver will work only once, and subsequent calls to deliver will just silently return nil. Right? So you can have code that speculatively tries to deliver, and whoever wins, whoever gets there first can win. And again, you can dereference these the same way. You can wait with a timeout and an or else value, or you can deref them and be very cavalier about it and be willing to wait forever. So, I'm going to digress for a moment and talk about some things that are not on the slides because they're not part of Clojure. I would argue that the biggest mistake, let me back up and say a little bit about myself. I've been doing concurrent programming on and off since the mid-90s. I consider myself reasonably competent at it, which means that I should be carefully code reviewed and tested, like most everybody else. And when I first learned Clojure, this is probably an innate part of learning anything. I went through this phase where I tried to use Clojure's concurrency constructs for all concurrency work I did in Clojure. If you think about that sentence, it's sort of a sensible thing to try, right? I'm doing something concurrent in Clojure. Clojure has concurrency constructs, therefore I should use them. Well, the fact of the matter is that Java util concurrent has a bunch of really rockin' concurrency constructs if you're writing low-level concurrent code, including the various atomic values, atomic integer, atomic long, those guys, including Java util concurrent semaphore, a big favorite. What's the other one? Countdown latch. There's a whole bag of Java util concurrent tools that are really great, and they are not exposed in Clojure because when Rich was writing the language, he felt no need to expose them because they work perfectly fine from Java, and Clojure's Java interop is great. Now, the potential problem with that is if you look at Clojure's concurrency approach and say, well, I expect that to be a comprehensive solution, and you find that there's nothing in there that corresponds to a semaphore, and you try to build a semaphore yourself without using Java semaphore, you're going to be in for potentially some pain. So this is not everything you need when you're writing low-level concurrency stuff. There are other pieces that you're going to want, things like semaphores and countdown latches in particular. You're still going to use them. As an interesting example, in writing Datomic, a database, you can already guess, based on what I said before, how many times I use software transactional memory to implement a database. 0. I used Atom quite a bit. So your local copy of the database value is actually in an Atom. And so when you do a transaction, it actually uses that exact model to say, take this Atom, which points to the current value of the database, and functionally move it to the next value of the database, which is really super amazing. There are several places in Datomic where we use countdown latches. And there are several places in Datomic where we use semaphores. So it's not the case that this represents everything that you need. I do think it's the case that this programming model represents everything most application programmers will need while they're programming at the application level. Right? While you're not writing plumbing, this is a fairly comprehensive set. So where are we? We have this unified succession model where we make references. So we make these protective things around a sequence of values. We assign those references to values. And then over time, we functionally transform one value to another. And then we have atomic succession. Right? That's it. Just go back to these 4 slides. Right? You can take that and apply it to dozens of different APIs in Clojure and say, here we are, and we have values, we apply functions, and then we succeed. So I have a repository on GitHub that has all the different presentations that I do. Right now it has an abstract for this presentation, but later tonight, or more likely tomorrow night, I will post the slides from this presentation along with the corrections on that, the stuff about the unified succession model or the various instantiations of it. I'd like to talk for a few minutes about parallelism. So the other side of the coin. We talked about concurrency and putting all these pieces together. Parallelism is really about organizing your work with the right amount of coordination. And the important thing is that it's not too much coordination and it's not too little. So imagine that I am a commander in an army and I have 20,000 soldiers and I want those soldiers to move across a bridge. And so I take a traditional imperative programming language approach to moving the soldiers across the bridge. I say, for soldier and soldiers, soldier.crossbridge. Okay. What I've actually communicated to my underlying programming languages is what? Each one of those soldiers should cross the bridge one at a time in a particular order, and those soldiers should start crossing the bridge before the soldier before them has finished. Right? So it's synchronous, it's chained, it's in order. This comes from, if you think back to the slides where I talked about, we have this model from the 1970s where memory is expensive and disks are expensive. And then there was that maybe slightly non sequitur one at the bottom, this presumption of complete control of the machine that we're running. This notion of I'm going to do things and control at that level is this really fiddly, I'm a hobbyist working on my box and so I'm going to do that. And it's not a very suitable notion for massively multi-core boxes and distributed systems. What do I want to say as the commander trying to get these guys across the bridge? What is my real instruction? Semantically, what would I really like to say? Everybody get across the bridge, right? As quick as possible. And there's a lot of details that then, come into play. So maybe, and maybe we should step back another step from that, right? I want everybody to get across the bridge as quickly as possible. But actually, one of my underlings comes up to me and says, there's a boat down there and there's another bridge that's less than a half a mile away. Isn't what you really want to get the guys to the other side? And shouldn't some of them go over and use that bridge and some of them use the boat? Oh, okay. Well, that sounds like a pretty good idea. So I decide that we're going to use both bridges. And we look at the 2 bridges and we divide the soldiers up. The bridges look approximately equal. So we send 10,000 soldiers across this bridge, and the other 10,000 soldiers head down to the other bridge that was pointed out to me. Now, it turns out that the bridge I picked to begin with is extremely muddy. And so the soldiers that are walking across that bridge can't move very quickly. And as we watch the process of getting these soldiers across the bridge, once about half of them are across, we realize that the other bridge is already empty. So what should we do at that point? We should send the soldiers over to the other bridge if our goal is to get across the bridge as quickly as possible. Now, Java has, since Java 6, has that technology for switching the soldiers to the different bridge. What's it called? Forkjoin. Right? Forkjoin says, I'm going to take the soldiers and I'm going to send them to the, and it says, I'm going to do it for you. Right? You set up your task and say, I got to get all these guys across the bridge, but we're going to send those soldiers there for you. And Clojure, on top of Forkjoin, builds, what is it called? It's reducers. So Clojure reducers model that idea. So the idea of a Clojure reducer is that you're going to take a job and you're going to pass it off to this reducer, and it's going to say, I'm going to decompose the job. You don't care about the order in which things get done. So you're not saying, I want to do all these things in order. You say, I have this work that needs to be done with all these things. The reducer is going to split that up, and then it's going to let Forkjoin reorganize that work, and maybe if one thread gets faster for whatever reason, get that work done over there. There are other things that you want to think about, though, when you're taking a system and making it parallel. Another thing that you really want to have is laziness. Right? I don't want to say, from a modeling perspective, get all the soldiers in memory. For soldier and soldiers, do something if the number of soldiers doesn't physically fit in local memory. So here the analogy starts to break down with the real world, but roll with it for a minute. Right? You want to have some way to say, work across this collection, but do it in a window. Right? Go in a window across, do this work with this group that I can fit in memory of some suitable size. And Clojure has that built in across all of its collections with what's called the sequence abstraction. So the sequence abstraction by itself doesn't help you go and parallelize things, but it does put you in a position to start a bunch of parallel tasks, each of which are going to work with this window. And then reducers build on top of that to give you the parallelism that you want. And there are other ways you could do it. There are other less awesome ways than doing it just with the reducers. So there's parallel map on top of map and things like that in between. But the real end game, at least right now in the Java ecosystem, is being able to use Forkjoin and be able to use it natively. One of the nice things about Clojure's approach to reducers is that we don't believe that data structures are inherently parallel. Some languages will take data structures and say they have to become parallel in order to be used with Forkjoin. Forkjoin works with Clojure's data structures out of the box. So there's not a special kind of collection to do this. You work with your ordinary collection, you don't know how to use reducers, and then one day you wake up and you realize you have a performance problem, and then you adopt reducers, and your code doesn't change except for at that one spot where you say, now start using reducers for this, and everything's grand. So the other thing I want to say about the succession model, and this is super important, right? So first off, let me just say that we've done a talk on Clojure concurrency, and I haven't showed you or told you the names of the functions you would need to use to do software transactional memory. Right? I mentioned the ref type, but I didn't and I'm not going to say it now. It's really hard to think about a word and not say it. But I'm not going to say the name of that API because I don't think it's that important. Right? And I want you to go away from this. You should write on the evals, I came all hot and bothered to learn about software transactional memory, and the presenter wouldn't even tell me how to use it. Right? It's really easy to use. Right? You call this function that I'm not going to name, and then you put a bunch of changes in it, and they're all inside a transaction. It really is kind of mind-numbingly simple to use. But the important idea is the model. And the reason that I want you to go away with this is that if you come away today with this notion of values, references, and a unified model of succession, that's actually a way of thinking about building programs. And it's a way of thinking about building programs that is ready for concurrency and ready for parallelism. And when I hear people talking about this, instead of talking about a model, they're almost always talking about techniques. And two techniques that people get all excited to talk about are software transactional memory and actors. Neither of those is a model for building concurrent systems. Neither of those is a model for building parallel systems. They are implementation techniques within an overarching model. And the overarching model is the thing that you want to understand. Now, I deliberately chose to make this talk relatively abstract and light on the code. The longest code snippet was 2 lines. And I think it's a testament to the power of Clojure that you can get across these ideas with these little tiny snippets that really are, all the work of doing the job. And the feeling I had when I was writing Tomic, and we got to the sort of inner function that actually updates the entire database, which could be gigabytes and gigabytes of data, and it's just swap database function that applies a transaction and gives you the new version. I was like, oh man. And that in itself is a really important idea, because one of the reasons people think that they need software transactional memory is that they think they need that coordination. They need that coordination because they're working with 2 things. But if you take those 2 things and put them in one data structure, you don't need coordination anymore, right? You just need an atom around that data structure because the coordination is managed by the data structure itself. It's not managed by the coordination framework outside it. And that's a really important idea, and it gets to how you model systems, right? So if I were going to model this room of people, and it was a group of people that could change over time, people could come and go during the talk, then I would use a set as the data structure, right? Logically, we are a set of people, and I would put that set inside of an atom. And then if somebody came in the room, I would say, swap bang, people in the room, conj, new person, C-O-N-J. And conj takes a collection and efficiently adds a new member to it. And it's polymorphic across the different collection types, but it does the right thing with different collection types. If I then had somebody leave the room, I would say swap bang, people in room, disj, D-I-S-J, disjoin, remove that person from the collection. And so even though there's a bunch of things, there's no coordination needed. Where you get into needing coordination is what if we said we're going to track this room and the other rooms in the conference. So now, if somebody leaves one room and comes in the other, we may have a rule that everything has to tally up, right? You guys are being watched by Big Brother, so everybody has to be somewhere. And so when you're removed from one set, where do you end up? Somewhere else, although we have a problem, right? We probably have to model being in the hall and being in the bathroom and all that stuff, but let's set that aside. Let's say that you magically transition at least from one room to another, so we'll ignore the rest of the problem. So now you're like, well, wait a minute. I probably need software transactional memory now because we have all these different rooms. So I'm going to put each different room in a ref, and then I'll start a transaction, I'll take you out of one room and I'll put you in the other room. But I could have a map that's keyed by room, and then it has a set of all the people in the room, and then put that in an atom. Right? So there's still not a need to go to a ref. And of course, this can get bigger and bigger and bigger, and eventually you end up with something like the Datomic database, where an entire database is in the atom. So I can manage arbitrarily large things without need for coordination with that thing and something else. I'm not saying that coordination across things is never needed, but it's important to think about minimizing the places where that kind of coordination is needed. So now I'd like to open it up to questions. So the question was, has the Clojure community come to a consensus on when to use STM? I think that if you look at like the State of Clojure survey and you see the kinds of things people are building, the answer for when you would use the STM is really quite rarely. Right? If you're building a web application, I just can't think of a situation off the top of my head where you're going to need this. If you're building an application, and the plain reality of it is that you find that as you're using Clojure, you need very few references of any kind in your system. So the functional programming people have the right of it, right? 99.4% of your code should be functional. And the number of references you need to begin with ends up being extremely small. And so it really is a matter of, if you find yourself in a situation where you need to model in-memory transactionality, and you don't care about persistence, right? Because there's no bridge. Bridging STM to durability is a research topic at this point. And so there's no bridge from STM to that. So if you need durability, you're going to use your traditional database. And frankly, in the absence of having Clojure's programming model, most people have punted and essentially rely on databases and other durable things to give them all of their concurrency semantics, because they don't have concurrency semantics in their language. I'm going to say that again because it's really important. Right? People don't really have semantics for dealing with concurrency and parallelism in their language, so they punt the job to a framework or to a persistence system. Persistence systems have to have concurrency semantics, although some of them are almost non-semantically, terrifyingly wide open. But they punt to those places, and so programmers just get out of the business of even hoping that their language can do these things. Yes, so the question is, what's the difference between a promise and a future? When you do a future, you are saying right then, do this work somewhere else. And you're saying, go schedule a thread to do this work, and then people can come back and do it. When you make a promise, nobody starts doing the work. It's just sitting there, and it doesn't get done until a deliver happens. So I'll give you an example of where a promise is used in Datomic. So under the covers, Datomic is asynchronous and queued everywhere. Right? So everything is in there, and there are chains of queues for performance and protective, boundaries in there, so that if things go wrong, they can't sort of infect the rest of the universe. And so when you submit a transaction in Datomic, you're sitting in a peer, and you're like, okay, I want to send a transaction, and it's got to go over to the transactor who's going to eventually commit that to storage. When you submit that, that thing gets a GUID, and that GUID is a key in a map that's associated with a promise. Okay? Now, that promise is going to be filled as a result of the transaction completing, but that's a long way away, because right now that transaction's data sitting on a queue. There's a worker that takes data off that queue and puts it on the wire over to the transactor. On the transactor, there's a series of tasks that happen. Deserialization, processing of the transaction logic, ensuring of invariance, making sure it's written to the log so it's actually durable. And then eventually, a message goes on another queue back to the peer. And then the peer, when it receives that, you don't see this at the application level, but the peer is watching the queue. When that message comes back, it fills the promise. If that promise is not filled, and it fills it with the results of the transaction, so you can actually go back and find out what happened. If that promise is not filled, then you can wait for it in timeout and go, well, I don't know if my transaction succeeded or not. Right, which is the best you can do with talking to another system. Right, you can know if it did succeed, but if you don't get any answer, you're going to have to go to some out-of-band mechanism. So that's a good example of using a promise. So if you look at the Datomic peer, the thing that represents the database connection, it uses an atom to hold the database value, right, whatever the current value of the database is, and it uses well, there are various places it uses semaphores to limit the amount of threads that will get going. It's both soft and hard limits on the amount of threads that will get going. And it uses the promise to sort of set that these things are going to come back. Now, it's also a good example of not everything is provided in Clojure, because what happens to that map of keys and promises if you're not getting answers, but you keep sending stuff? It gets arbitrarily large. Right? So that map is actually currently a Guava cache with timeout. So if anybody uses Google Guava, rockin' Java library, right? It has caches and timeouts. So Clojure doesn't have a cache with timeout library, and the great thing about building in the JVM ecosystem is you don't have to build every different thing you might ever need to write programs. If there's a good library in the Java ecosystem, you can use that. And so we use Guava for that, and in places where we want to keep track of things and let them time out. Why did I write Datomic? The question is, why did I write Datomic? Rich Hickey made me write Datomic. He locked my family in a cellar and told me that they would not be set free until I helped write Datomic. No, so Datomic started, I got interested in Clojure in 2008, and I was acting as a technology scout for Relevance, my company, and we had adopted Ruby in 2005. And had felt great traction from being early adopters of something that got popular later. And that was kind of accidental. And so we said, okay, we'd like to have a more deliberate approach to new stuff. Let's go find something that's going to become hot and do a little research. And so I did evaluations of JRuby, Groovy, Scala, Clojure, and Phantom, and fell in love with Clojure, liked all the others, right? My advice is, if you're in Java, get help somewhere. Right? Go use one of these things. But really loved Clojure, and so started using that, and met with Rich Hickey to talk about building a commercial entity to help organizations adopt Clojure. And at the end of that meeting, he said, would be pleased to be in business with you, and it would be great to build that entity and help the community and whatever, but let me show you on the whiteboard this idea I've just been thinking about a little bit. And so he sort of drew the picture of how Datomic worked, and my draw just ratcheted down, sort of notch by notch by notch. And at the end of about half an hour, I said, okay, can we drop everything and make one of those, please? So it is entirely, it's entirely a labor of love, and it really represents an attempt to bring the semantic model that Clojure has in memory into the data tier. And we're hoping a ton of people will follow us. There are a lot of Datomic's ideas that could be adopted in part in other databases, and there are other semantics. So as I said, we have these reference types with different semantics in Clojure. You could have other reference types besides Datomic connections that were databases, that had different semantics, that had different persistent strategies, and so forth. So it would be exciting for us to see other people jump in the pool and be there with us. I'm not sure if I actually answered your question, because that's a pretty wide open question. Does that cover it? So question is, comments on Clojure versus Go for concurrency stuff. I don't really have more than a flyby knowledge of Go, certainly written and used by smart people, so I would expect they do a good job. Surface skim is that it's operating at a lower level and closer to the hardware, so that there are going to be things that they're going to be able to do that we couldn't. The flip side is there's going to be a level of abstraction that keeps you as an application programmer out of the woods using something like Clojure. I mean, to be fair, I said, everything about this model, if I didn't make this clear before, is predicated on garbage collection. Right? You can't implement a model like this without garbage collection. A model that says we're going to use new places for new memories, new places for new records, new places for new times. And so if you're in an algorithmic scenario that's just out of bounds from a performance requirement characteristic, then this whole model doesn't make sense for you. And if you look at the, my lay observation about the number of people who are still using C or C++ instead of moving to a garbage collected language is that 75% of them are probably nuts, and they should be working at a higher level of abstraction. And the other 25% really need to be there because they're doing stuff that needs those kinds of that kind of low-level performance guarantee, and they can't take going a notch up the abstraction ladder. So the implementation of, you're talking about Clojure software transactional memory right now, right? Yeah. So the implementation of the SDM is a very savvy implementation, and it has barging, and it has the ability, it tries to prioritize getting people in that were there first and so forth. So there are not a lot of reports out in the wild of people having problems at the plumbing level. So there's sort of two ways to interpret your question. How do I debug it if I think the SDM is broken? And how do I debug it if I think I did something wrong? I don't think the SDM is broken, and people haven't, and it's not, people are not necessarily using it for enormous things either, but, Cliff Click has tested it on big Azul hardware and seen, although he's critical of it, he's seen decent performance and not it falling over and dying. In general, I would say that I'm giving a talk tomorrow, shameless self-promotion, called Clojure in the Field, where I talk about obstacles and hurdles and opportunities in adopting Clojure. And certainly one thing that always gets pointed out with a young language is debuggability. It's a challenge. And I think that the challenge, and particularly with concurrent systems, I think that if you look at the literature on software transactional memory, a lot of people have tried to use it as magic fairy dust on top of mutable things. So in addition to being a software transactional memory system, it also has to do magic keeping track of things that might be mutating underneath it. And so a lot of the critical stuff you'll find on the internet about it is about STM without an underlying model of succession and values. And so there really isn't a lot of academic or other treatment of an STM like Clojure's, unfortunately. It would be nice to gain more experience. I don't personally find the state of debugging tools in Clojure to be a problem, but I know other people do. So, I mean, it's fair to say that it's a challenge. It is possible to connect JVM debuggers to Clojure. The challenge there is the programmability of a JVM debugger, particularly in the face of lazy collections, right? So if the debugger is used to, when you hit the widget, opening and displaying a collection, and you have a lazy Clojure stream over 1 trillion things, then the debugger is going to suffer. Right? So, and as far as I know, nobody has gone, and you could do it, right? The wire protocol for writing a debugger and all that stuff in Java is public documented stuff. But I don't think anybody has written a kick-ass graphical debugger that targets Clojure specifically, which would be an awesome thing to do if you're not busy tomorrow. So the question is, what is the overhead of implementing a large application in Clojure due to garbage collection? There is no one-size-fits-all answer. There are going to be application loads that are, like with any system, right? You can find a perverse combination of things that's going to be bad. But you have to, when you're doing these calculations, you always have to consider the trade-offs on both sides. So a Clojure or other functional system is going to produce more garbage doing the same work. But it's also going to have less coordination for reads, right? So all of these values have this promise that you don't have to do coordination. That's a form of overhead as well, and coordination, when done incorrectly, leads to deadlock and other kinds of pain. So there are trade-offs on both sides of it. My finding has been that if you can make it perform in Java, you can make it perform in Clojure. And that's really a key design principle of Clojure. One of the things that Rich says is, I did not write Clojure to replace Python or Ruby in my day job. I write Clojure to replace Java in my day job. So it is an explicit goal of Clojure to be able to perform enough like Java that doesn't become a problem. So the question is, where do I see Clojure going? So I see Clojure as the ideas behind Clojure, and let's call them Clojure branded ideas because it was the name that got there first, broadening their reach. So the first salvo of that was Clojure Script. A second salvo of that was Tomic. Another couple of salvos there are Eden and Freshen serialization formats. There's a whole set of tools out of which might emerge, dare one say it, a stack that allows you to build Clojure applications and target all up and down. It's a resourcing question. In order to do Android well, I think that the right approach is to take not Clojure but Clojure script, because Clojure script is a Clojure compiler written in Clojure that currently targets producing JavaScript source as its output, but make that compiler retargetable and make it emit something that is Dalvik Android friendly, and then use that as the language on Android, right? And be out of the JVM Java business entirely. That's the direction I would go to get there. It's certainly one of many things on a giant world domination plan I have on the wall at home, but I don't have any commitments on resourcing or timeline for that particular one. But I think that, the important thing here, if you believe anything about what I've said today, and you should believe about 48% of it, but I'm not going to tell you which 48%. If you believe anything about what I said today, this is a sea change, right? Modeling things with places. Is it going to go away? No. We're going to model things with places for all the same reasons that people still use C when they could use Java. There are always going to be people who need to work at that level. It's never going to go away. Or at least it's hard for me to foresee how it would ever go away. That being said, with the memory capabilities and storage capabilities that modern systems have, it is unequivocal that programming with places is the wrong default. And that almost every language out there and every mainstream language is on the wrong side of this stick. And so what do I see happening? Who knows whether Clojure wins, right? Ideas come along and then they get adopted in a lot of different places. But I would say 5 years from now, everybody will be using value and reference succession semantics. And hopefully other things I don't know about yet. But I think everybody will be using those things. It will be, not everybody, it will be the dominant way of thinking. It will be the default way of thinking. Once you start doing it, you really don't want to write systems the other way around. Right? I wrote a program in Java the other day and I had to worry that I had to get clone right. And I just put my head in my hands and wanted to cry. Like, that kind of stuff is so low level and primitive if you're doing application development. You just don't want to be there. All right, well, my name is Stuart Halloway. I hope you've enjoyed this. This is my first time at DevNexus. I really appreciate the chance to speak to all of you today. I'm giving 2 talks tomorrow. I'm giving a talk on Simulant, which is an open source framework for simulation testing. If you were thinking that you haven't spent enough time writing testing code for your application and like to look at a new way to do it, I'd love to see you. And then I'm also giving a talk, Clojure in the Field, that talks about experiences adopting Clojure and challenges adopting Clojure. Thanks very much. Have a great evening.